Good morning, Professor and colleagues. My name is Dengwu Jiao, and I'm from City University of Hong Kong. First, I would like to give my deep thanks to the Rilem committee for offering me this 2025 Gustavo Colonnetti medal. It is my great honor to be here to give this presentation. I obtained my PhD in Dengwu University, Belgium, and Hunan University in China. And the topic of today will be the rheology control of cementitious materials, which was also the main research topic during my research career up to now. I will share some results obtained in our research group in this subject. First, about rheology. It is the study of deformation and flow of materials. When it comes to concrete materials, the rheology plays a most significant influence on guiding the concrete miniature design, and it will also influence the plating process, like the transporting, pumping, and formwork cutting. Well, the requirements of rheological properties depends on the operations. For example, in the pumping process, it demands a high flowability of the concrete material, and if a short interruption is occurrent, a high structural buildup will increase the pumping pressure and even cause the blocking phenomenon. Well, after the concrete is cut into the formwork, a high structural buildup will reduce the formwork pressure. So this means the requirements of the structural buildup in the pumping and cutting process contradict with each other. And the contradicting rheology requirements also exist in 3D concrete plating. On the one hand, the concrete material needs to flow enough to be pumped and to be extruded. And on the other hand, after the material reaching the final position, the static yield stress should be high enough to withstand its shape without deformation. So this means we need to strike a good balance between the rheological properties and the stiffness for the same concrete mixture. So this highlights the importance of rheology control. Generally, we have two options to achieve the rheology control. First one is passive control. Based on the relationships between rheological properties and the material proportions, we can obtain the desired flowability and rheological property by adding minerals or changing or chemical admixtures. And this requires an in-depth understanding of the rheological and viscoelastic properties of cementitious materials and their different influencing factors. Well, why I call this method is passive is because after the mixture proportion is determined and after the material is prepared, no further intervention is possible to adjust its rheological properties during the placing process. Another method is active control. The concept of active rheology control was proposed by Professor Schutter via the ERC Smart Cut project. To achieve active rheology control, we can pre-mix some special admixtures in a concrete material, and without triggered, this admixture is in an inactivated state. But if we apply a trigger signal, this admixture will respond to the signal, and it will help us to achieve the regulation of the flowability and the rheological properties of the concrete material. And the active rheology control can be used to regulate the rheology of post-mixing concrete. And to achieve this, we need to get a fully understanding of the rheological and structural response of cementitious materials and the external signals. So today I will present some research results on these two areas. First one, we studied the influencing factors of concrete rheological properties, like the mixture proportion parameters in this slide about different superoxidants and different cementitious materials. And to understand and to explain the mechanisms, we can correlate the rheological property to the particle packing, absorption behavior, and also the hydration behavior of the system. So in this way, we can get a better understanding of the change and the evolution of rheological properties and the different influencing factors. And because the placing process will pose different shear rates on the concrete material, so the shear history also affect the evolution of rheological properties. We measured the rheology of cement paste and concrete and the continuous shearing. We can say the thixotropic behavior and the shear thinning and shear thickening phenomena are highly related to the shear rate we applied and the cementitious compositions. And we can also explain this behavior by creating to the physical nature and hydration behavior of the system. So these results will help us to maintain a good flowability during the placing process. And in addition to the rheological properties, we also evaluate the viscoelastic properties of cement-based materials by using the small amplitude oscillatory shear test. We use the storage modulus at the linear viscoelastic range, the critical strain, and the elastic stress to describe the stiffness of the paste, as well as the macromechanical strength of the interparticle connections. And then we studied the different influencing factors on the viscoelastic behavior. And here there is an example shows that the relationship of the critical strain and superoxidic dosage. And here we can say if we incorporate a high content of superoxidic, we can obtain a higher critical strain. This is because of the increase in the interactions and entanglement effect of the superoxidic modulus absorbed on the solid particles. And high superoxidic dosage will reduce the viscoelastic stress. This is because of the reduction in the storage modulus at the linear viscoelastic range. So this result will help us to control the rheology and the stiffness of concrete material. And we also explored the application of rheology in guiding concrete miniature design. We proposed a rheology-based miniature design method. In this method, the particle packing and the aggregate fraction are determined based on the closed packing theory. And the optimal binder content is determined according to the excess paste thickness theory. And we use the simplest centroid design method to establish the relationship between ternary cementitious compositions and the concrete properties. And finally, we can determine the optimum cementitious composition with multiple property requirements based on the overlap area of the desired parameters. So this rheology-based miniature design method can reduce the usage of cement, and it can also reduce the reliance on the traditional empirical workability assessment method. And we also studied the application of rheology in 3D concrete plating. We designed a device to measure the deformation value of printed layer to simulate buildability after extrusion. And by establishing the relationship between deformation and evolution of static yield stress, we developed a rheological method to measure the buildability. And recently, we also trying to apply the rheology-based miniature design method to develop the sustainable concrete by incorporating recycled waste powders and recycled aggregate, and the results will be available soon. And this is the part about the passive rheology control and its applications. Now let's move to the second part, active rheology control. We evaluated the typical rheological response of cement paste by using a parallel plate rheometer equipped with a magnitude rheological device. And these are the typical results for the pure cement paste and the paste containing magnetic nanoparticles. We can say if we apply a magnetic field to the pure cement paste, it will not affect the evolution of the storage modulus. But for the paste containing nanoparticles, we can say the storage modulus at the early age is reduced, and after longer time, the storage modulus is increased. This means applying a magnetic field to this paste it will improve the early liquid-like behavior, and it will increase the solid-like behavior after longer time. The difference between these two pastes is because of the low magnetic properties of the porcelain cement particles compared to the magnetic particles. And to explain the rheological response of cement paste, we proposed a hypothesis of the nanoparticle movement and cluster formation. Specifically, when we are applying a magnetic field to the cement paste, the magnetic nanoparticles will try to move to contact with each other under the magnetic force. During their movement, it will create a macro-agitation effect. This will destroy the connections between the cement particles and release the potable into the water. So that's why we observed the early increase in the liquid-like behavior. And the magnetic particles will form chains and clusters in the cement paste, and this will increase the stiffness of the paste. To verify this hypothesis, we derived the calculations about the magnetic force and the moment velocity. We proposed a concept of the magnetic yield parameter to describe the relative value of magnetic force and the resistance of the suspension. If the magnetic yield parameter is higher than 1, it means the magnetic force will overcome the resistance of the suspension, so the nanoparticles will move in the paste, and it will form the clusters, and the paste will show clear response. By contrast, if the magnetic yield parameter is lower than 1, this means the matrix will prevent the movement of the nanoparticles and also prevent the formation of the clusters. So the paste will not show the response. And we also estimated the moment velocity by equalizing the magnetic force and the viscous drag force. And we calculated the magnetic yield parameter and the moment velocity for the typical cement paste under magnetic field. We can say the magnetic yield parameter is far higher than 1, and the moment velocity is comparable to the particle distance between two neighboring nanoparticles. So this result indicates if we apply a magnetic field to the paste, the nanoparticles are indeed move in the paste, and it will contact with each other in a very short time. And these calculations provide a verification for the movement of nanoparticles. To verify the formation of magnetic clusters, we prepared hardened samples for SEM test, and then we obtained the every element map by using the EDS. And here we can say for the paste after treated by magnetic field, there are some clear clusters of every element. The every element cluster indicates the clusters of nanoparticles. And to quantify this clustering, we use the image analysis technique to convert the every element map into the distribution of the every element number in different cells. And then in this case, we can quantitatively describe this clustering by using the coefficient of variation value from the statistical method. And from the result, we can say in some cells, the number of the every element are indeed higher than the average value. And when we apply the magnetic field, the COV value, the coefficient of variation value is increased, and there is a linear relationship between the magnitude rheological response and the relative change of the COV value. And this clustering results provide a solid verification for the formation of magnetic clusters in cement suspension if we apply a magnetic field. And afterwards, we studied the influencing factors of rheological response. Like here, it shows the influence of particle size and the magnetic properties of nanoparticles. We use the 3 different magnetic nanoparticles. And we can say the particle size only affects the structural evolution without magnetic field. Well, in the presence of magnetic field, the structural buildup is mainly determined by the magnetic properties of the nanoparticles. And we also established the relationship between the calculated parameters and the measured rheological properties. We can say the magnetic yield parameter can be used to predict the stiffness of the paste, and the moment velocity can be used to predict the early increase in the liquid-like behavior. And this is the influence of cement-based medium on the response. We can say at relatively low solid volume fraction, the response is insignificant. This is because the large particle size between the solid particles in this system. Well, at a relatively high solid volume fraction, the response of the paste also becomes not clear. This is because the dense particle packing system will prevent the movement of the nanoparticles. So this result indicates there exists a suitable solid volume fraction for the cement paste with a very clear response. Beyond the mixture proportions, the magnetic field itself also affected the response. We can say low magnetic field strength will not change the structural evolution. And when we increase the strength of the magnetic field, the early decrease in the storage modulus and the increase in the storage modulus after longer time are increased. And we also studied the influence of time-varying magnetic field. We can say if we apply a magnetic field to a resting paste, we can observe a sudden drop in the storage modulus, and it will increase significantly afterwards. The sudden drop in the storage modulus is because of the nanoparticles movement under the magnetic field if we apply the magnetic field. And the formation of the magnetic chains or clusters will be responsible for the significant increase in the storage modulus. And here we can say if we reduce the magnetic field from a high level to a low level, we can also observe a drop reduction in the storage modulus. This means the magnetic clusters in the paste are reversible. So if we remove the magnetic field, it will reach the original state, but the growth rate of the storage modulus will be higher than that without magnetic field. This is because there are some residual magnetic clusters exist in the suspension because of the remnant properties of the particles as well as the viscoelectrical properties of the suspension. And the shearing also affects the response. We measured the flow curve under the magnetic field, but we observed the phenomena of bleeding and nanoparticles agglomeration on the interface between the cement paste and the upper rotating plate. And we hypothesized that this behavior is because of the particles movement and the migration and the combined effect of magnetic force and the shearing. And to verify this hypothesis, we also measured the concentration of magnetic particles in different regions by using the VSM test. And because of the limitation of the high rate shearing, we evaluated the change of apparent viscosity under low rate shearing at 10 per second. We can say at a higher magnetic field, the paste will respond to the field very quickly, and the viscosity will be increased significantly. The increase of the viscosity is because the magnetic force will dominate the hydrodynamic force induced by the low rate shearing. And when we remove the magnetic field, we can see the viscosity will reduce to the level without magnetic field. This means the residual magnetic clusters may be completely destroyed by the low rate shearing. And we also explored the response of traditional minerals like flash. We use 4 kinds of magnetic flash, and from the rheological test, we can say different flash cement paste will show different degree of the response. This is because of the difference in the magnetic properties, their particle size, particle shape, and also the surface texture. And we also try to apply the calculation of magnetic force to the flash cement paste, and we discussed the different cases to determine the particle distance and magnetic properties, and we also established the relationship between magnetic force and the rheological response. Next is some potential applications of active rheology control. We can use active rheology control to achieve on-demand structural evolution. To achieve this, we can add some magnetic particles in the paste. And if we want to speed up, if we want to increase the structural evolution, we can apply a constant magnetic field. Well, if we want to slow down the structural evolution, we can apply a pulsed magnetic field. And by changing the type and the strength of the magnetic field, each value in this green area could be possibly achieved. Well, for comparison, the reference paste can only develop according to this black curve. So this provides a typical example to achieve the structural evolution using magnetic field. The next possible application is in pumping process. We designed a homemade magnetic control unit and to replace the original pipeline. And we can say if we apply a magnetic field, the pressure loss will be changed significantly because of the formation of magnetic clusters. And we also derived the constitutive models for the active rheology control, and we verified this model by using simulation and experimental results. The next application is the controlling formwork cutting process. We also developed a simple setup to study the pressure-driven flow through a confined geometry. And from the results, we can say at a relatively low pressure, applying a magnetic field will totally block the flow. And even at higher pressures, applying a magnetic field will reduce the flow rate. So these results will help us to reduce the formwork leakage during the casting process. And another application is 3D computer plating. We use the Rheolometer test to simulate the 3D plating process by giving different sharing and measure the structural buildup. We can say even we apply a very short magnetic field at the end of sharing, we can observe a higher structural buildup in the later stage. This means we can possibly enhance the buildability of the printed layer if we pose a magnetic field during the extrusion process. But this is just a conceptual method. Currently, our group are conducting the real 3D computer plating test to verify this method and also to address some potential other issues. And next, there are some results obtained recently. And you may be curious about whether applying a magnetic field will have an influence on the microstructure or the mechanical strength. So for this purpose, we use SRD and SEM to evaluate the early structure and hydration products. And we can say if we apply a magnetic field, it will have no significant influence on the main type of the hydration product. And the magnetic particles will not engage in the hydration, but the movement of the magnetic particles will form weak zones between the magnetic particles and the matrix. So this weak zone maybe have a negative effect on the mechanical strength. And the early compressive strength also shows anisotropic behavior along the direction of the magnetic field. And now we are also conducting some macrostructural tests to analyze this, the mechanisms behind this mechanical anisotropic behavior. Another one is we studied the rheological response of cementitious materials by using steel fiber as the responsive component. We can say if we apply a horizontal magnetic field, we can observe a directional flow behavior perpendicular and vertical to the magnetic field. And we also measured the concentration of steel fibers in different regions for the post-methane concrete, and these results is in agreement with the flowability test. And to further study the directional flow behavior, we also use the image analysis to measure the the fiber distribution and orientation in cement mortar and concrete. And these results have been drafted to a paper to submit for under review. And this is a short summary of my presentation. Generally, we have two options to achieve the rheology control. For the passive rheology control, it can be achieved by changing the material compositions, and it can be used to develop the cementitious materials with desired fresh properties. But it cannot change the rheology of post-methane concrete. And the rheology-based methane mixture design method can be used to develop the high performance and sustainable concrete. For the active rheology control, it can be achieved by adding magnetic particles and applying a magnetic field, and it is promising to make the plating process more reliable and smarter. And we are conducting some ongoing research to explore its possible application in 3D composite plating and developing multifunctional concrete. And I would like to express my deep gratitude to Professor Hilde Schutter and Professor Cementitious for their invaluable guidance and support over the last years. My sincere thanks also goes to my colleagues at Beijing University, Colonnetti University, and the City of Hong Kong for their collaboration and encouragement, and the financial support from the ERC, UGC, SFC, and other agencies are highly acknowledged. This is my presentation today. Thanks very much. Thanks again for inviting me to give this lecture, and I'm looking forward to the discussion and potential collaborations. Thanks for your listening.